In prior discussions of chirality, we noted that a chiral object is not the same as its mirror image. For example, the mirror image of a left hand is a right hand, and the two are not equivalent since we can't overlay them perfectly. Although this analysis allows us to conclude that our hands are not identical or not the same, we know from intuition that in some respects our hands are the same, or at least they behave the same way. In this sense, our hands are isomeric. They're the same in some ways and different in others. The exact character of this isomeric relationship is stereoisomerism, since the hands differ only in the positions of the various parts of the hand with respect to each other, and not how things are connected. We've already remarked on a couple of occasions that the hands, and more generally the two mirror images of a chiral object, are related as enantiomers. The primary questions of this lesson are how can we make this determination systematically, what other types of stereoisomerism exist, and once we've made this determination of the isomeric relationship between two objects or two molecules, as the case may be, what can we do with that? What can we conclude about the relative behavior of the two molecules based on their stereoisomeric relationship? One of my favorite books about chemistry is called The Same and Not the Same by Roald Hoffmann, and the image on the cover is a suggestive image of a man looking at his reflection in a lake. The implication here being that the man and his reflection are the same in some respects and not the same in others. And this is the essence of the isomeric relationship in chemistry. Two molecules that are isomers are the same in some respects and different in others. For example, consider the two isomers of 2-butanol that I've drawn here. In many respects, they're the same. They have the same molecular formula, C4H10O in both cases. Ignoring the wedged and dashed groups at the stereocenter, they have the same connectivity. For these reasons, under some circumstances, they will behave the same way. For example, elemental analysis of both of these compounds will give the same results, since they have the same molecular formula. And many reactions of these two molecules will proceed in the same way because their connectivities match. Where they differ is in the configuration of this stereocenter, and in this respect, they're not the same. This is the essence of isomerism, both the same and not the same in some respects, but not the same in others. And really gaining a deep appreciation of isomerism amounts to answering the question, how? How are the molecules the same, and how are they different? Molecules with the same molecular formulas and the same connectivity but different configurations are known as configurational isomers, or much more commonly, stereoisomers. For example, the two molecules shown here are stereoisomers. It's impossible to perfectly overlay them so that all of their atoms and bonds match. To see this, examine the molecular models of these compounds shown here. The fluorine is indicated in light green and the chlorine in dark green. So we have set up these molecules so that they're looking straight at each other as we have in the drawings on the left. I can try to overlay these by translating the left-hand molecule over and then rotating around the other molecule to get the bonds between the central carbon and the methyl group corresponding. The way we have them aligned now, if I translate the left-hand molecule over just a little bit, we see that the methyl groups are essentially lining up, with a little bit of variation due to a slight rotation. Let's rotate around so that we take care of that, and now the methyl groups are lining up perfectly. But if we look at the chlorine and fluorine groups down here, we see that these are not lining up. No matter how we try to overlay these two molecules, we can never get all four groups attached to the stereocenter to line up perfectly. If we get two of them lining up, like the hydrogen and the methyl group, the other two will not. As a consequence, we can conclude that it's impossible to perfectly overlay or superimpose these molecules. They're not identical. They're stereoisomers. The other thing that's important to notice about this case is that the two molecules are mirror images, and the default view of these molecular models makes this clear. The molecule on the left is seeing the molecule on the right as it would see its image in a mirror, and vice versa. The molecules in this second example are also not identical, and the primary difference here comes at this stereocenter, where the hydrogen is pointing up and the methyl down in this molecule, but the methyl group is pointing up and the hydrogen down in this molecule. When we try to overlay these, you'll see that their groups don't correspond exactly, even when we try as hard as we can to line up as many groups as possible within the molecules. For example, if I color this molecule yellow and then I superimpose it on the other, we see that many of the atoms are lining up. The 5-membered ring atoms are lining up, and all of the hydrogens, and even the hydrogen in the methyl group on the left-hand side of the molecule are lining up fine. The problem is on the right-hand side of the molecule, where the yellow methyl group and the molecule that was originally down here is pointing down, and the CPK colored methyl group is pointing up. These two molecules are clearly not the same. The difference between the first case and the second case is that in the latter, the two molecules are not mirror images. And this difference is important for reasons we'll see in a bit. When studying stereochemistry and isomerism, it's important to be aware of situations where you're looking at the same molecule from two different viewpoints. This visual trick can cause the images to look different, suggesting that the two molecules shown are different. However, if we can rotate the molecules so that they superimpose perfectly, then we're just looking at two different viewpoints of the same molecule. Identical molecules we're going to call homomers, just to give a name to this situation when we're looking at the same molecule from two different viewpoints. An example of the homomer type situation is shown here. The molecule on the left is identical to the molecule on the right because they can be superimposed perfectly. If I take this molecule on the right and rotate it around this way, 180 degrees, I flip the ring over. That moves the methyl groups from a back-pointing position to a forward-pointing position on wedges. Clearly, this molecule is identical to the molecule on the left, and since all we did was turn the molecule over as a whole, we haven't changed it chemically in any way. We haven't moved any of the atoms with respect to one another. These two molecules are identical, and they're homomers. Although this idea of a homomeric relationship might seem silly, this will show up in certain types of stereochemical tests that we're going to look at in a later lesson when we become concerned with the question of stereochemical environments around groups within a single molecule. The last point I want to make about isomerism, and it's a really important one to think straight about how isomerism works, is that isomerism is a relationship, and as in any relationship, two molecules are implied here. Isomerism is a relationship between two molecules, not a property of a single molecule. And let me use a simple analogy to show this. We might, for example, in conversation say that this man shown here is a father. That implies the existence of a child, even if the child isn't mentioned explicitly. Anytime we hear mention that so-and-so is a father, we think automatically about the nature of that person's child, right? Even if the child isn't around explicitly. In chemistry, we often talk about a molecule, for example, having a stereoisomer or exhibiting a certain type of stereoisomerism. And this implies the existence of another stereoisomer, just as saying that this man is a father implies the existence of his child. To connect this to the chemical realm, you might see, for example, the statement that the molecule glyceraldehyde, which is shown here, exhibits enantiomerism. That's analogous to saying that the man in this image exhibits fatherhood, and that statement implies the existence of the enantiomer of glyceraldehyde. Isomerism is a relationship between two molecules, not a property of a single molecule.